Welcome back to Decouple for a very special, I was going to say live, but in person,
Definitely not live, but in
definitely not
person.
in person interview featuring my good friend, the JP 1000 and the Can Do Kid. Um, Joking aside, James Krellenstein and myself. James, welcome to the show.
Thank you. Thank you for having me at your house. And yes,
And the show's going to be a banger. We are going to be tackling the issue of AI and its implications on energy. Of course, focus on nuclear. This is a emerging area, and I'm really excited. I feel a bit behind the eight ball getting to it and covering it, but who better to explore it with than my friend James here? I've got a lot of thoughts and ideas down, and I'm going to attempt to do a little bit of an introduction to sort of ground where we're going with this, but as things classically go in decouple, we're going to go off on some tangents into the weeds. But basically, I view this situation. I mean, it seems to have come on us as a bit of a surprise, and even the developers, Sam Altman, recently saying that nothing short of an energy revolution would be required in order to power this new phenomenon. The emergence of a baseload demand, something that needs to be powered 24/7 in a set of societies in the West where we have been sort of fragilizing the grid and de-emphasizing baseload or even saying it's a myth. How this impacts on climate action. We have a recent report out from JP Morgan called Electrification, which talks about, we've added a bunch of capacity in terms of clean energy. Fossil fuels continue to grow, but we have, James might dispute this slightly, but we've failed to really electrify, certainly at the scale required for these ambitious or, frankly, other people might say unrealistic net zero goals. So we're going to sort of tackle that. I think we're going to try and get to what are some of the limits to growth for AI. It's fascinating to me that demand in the West certainly has been pretty flat for quite a while. Why that is and whether demand with AI is just going to continue linearly. I think that's a common human bias when thinking at the future, that trends will continue linearly, and that was certainly the mistaken thought of the utilities in the 70s and 80s. I guess up into the 70s when we were adding 4 to 5% per year of growth to the grid. All right. I mean, I'd originally conceived of this as a sort of the risk of kind of AI energy apartheid. I think we're going to go a little bit into what this, emerging massive addition of demand is going to mean for everyday people and human needs, and talk about some of the positives and potential negatives of AI. That's kind of way too big to go into scope, but we'll try and stay focused. So, James, a long intro there, but I just needed to gather my thoughts because I haven't been doing enough thinking about this. So again, warm welcome back.
Thanks so much for having me and for having me in your home. And we just came back from Bruce Nuclear Station 2 days ago and saw a Can Do in person, or a couple four Can Do's in person. So I think when we're thinking about computation, right, and computing, we don't necessarily think about computing energetically like we classically think of a lot of other things. But computing itself, just thermodynamically, does require energy. And there's something called Landauer's principle or Landauer's limit, which basically says that for a minimum, for any amount of computation, the second law of thermodynamics says a minimum amount of energy needs to actually be put in to actually do that computation. And that you just can't get around. That's first principle, second law of thermodynamics. Now, we should be clear that we're about a billion-fold away in terms of what that theoretical limit is and versus how much actual energy we are now spending to do a unit of compute. But what has been happening over the last decade or so is we have been seeing an enormous growth in not just computation power that's in our devices, whether it's computers or phones or embedded devices that just surround us, but also a huge amount that has been migrating to the quote unquote cloud, right? On rather than having the computing done locally, having actually the majority of the compute and storage out at some big data center and then transported to you through the internet, right, through fiber optics and whatever the last mile is, copper, but it's all being stored at a big data center. And we have seen compute use go up a lot over the past decade. But we've had also the amount of energy per unit compute decrease. And this is called Kumi's law, right? Back to the Stanford professor, Professor Kumi, who noted in 2010 or 2011 that it seems like about every 16 to 18 months, the amount of power that it takes per unit of compute halves. Right. So what has been going on simultaneously over the last decade, now it's maybe around 24 months, maybe as Moore's law starts to fail. But what we've started to see is that, yeah, compute load has been historically increasing. The amount of compute per capita, I don't know how we want to talk about it, has been increasing. But the actual amount of energy per unit compute has been decreasing at roughly the same rate. So we've been sort of running in place, right? We've been doing more compute, but the compute's becoming more efficient. And then, so therefore, the actual amount of energy use for data centers has been relatively stable. Now, we should be clear that from a baseline, the amount of energy use in terms of global warming impact, let's say, it's been estimated that, a minimum of 3.5% of humanity's GHG, global greenhouse gas emissions, are from data center-based operations. Wow. So that, according to these estimates, is more than shipping or more than aviation. Not combined, but single-handedly. That's just how much power is being utilized for compute in the regular status quo. And Amazon purports itself as to be one of the world's largest consumers of electric power and purchasers of electric power, just because Amazon, with AWS, is running such large data center operations. Now, what has happened over the last 24 months, and maybe a little bit shorter, is that we've started to see the AI boom occur. And in particular, in these large language models and more broadly neural network-based computing, rather than which is requiring a totally different architecture of compute. We've really gone from CPU-based scalar computing to really having a lot of these neural networks running on these large graphical processing units. They were originally historically GPUs, like by NVIDIA or AMD, but mainly NVIDIA. And there's two things that are going on. One is that we've lost a little bit, although we're better now on compute efficiency. But more importantly, and more broadly, the amount of computation that we need to be doing to do an AI-based task versus a classic non-AI-based task is just so much dramatically more. It's estimated, for example, that a Google search, a regular classical Google search, right, takes about 20 times less power than an AI-enabled Google search, right? And these are external estimates, peer-reviewed. That is a massive step change in the amount of energy that we're going to need to do for the same task. And that's partially driven by, we can pause there and talk about what is driving that. But what we're seeing is just AI is accelerating the amount of power that we need, right, to do these classical tasks. Right. And that's a huge thing.
So, you're talking about AI requiring 20 times the power per Google search.
But once again, the Google search might be a lot more useful and have much more utility. A Google search is a weird thing to compare it to. Right. Like, a ChatGPT query that you just normally do is taking about 10 times the amount of power that a Google search is. And that's just giving you the example of the step change that we're having in terms of compute use, which is translating to a massive increase in power use.
And the cynic in me, I was just looking up some stats. 20% of all internet searches are for porn. I'm not sure what percent is consumed by kitty cats. And obviously, I'm being a cynic here. There's a lot of highly useful applications, and I think people are talking about the potential for again a real productivity step change with the applications of AI. And I think we'll probably get into kind of what those are later. But yeah, with this emerging increase in baseload demand, let's talk a little bit about that. You've talked a bit about the scale, but how is it being met? We heard about this Susquehanna deal with Amazon. The tech companies had been, I think, a little reserved about using nuclear energy up until maybe they're being forced to now because of the nature of their demand and the scale of their growth. But Apple has claimed to be 100% powered by renewable energy in the past. Bit of a disingenuous claim, in my humble opinion. But where are we going with this? Because again, this podcast focuses probably a little too much on nuclear. We're going to get there. How are things currently really being powered, and what sort of conversations are emerging in terms of and how panicked are they in terms of meeting this burgeoning
demand? I think there's a couple things going on. We really have been seeing large growth in electric power use for data centers in, for example, the state of Virginia,
Mhm.
which in the United States has the most data centers. And for right now, at least, this is really, the AI revolution, while the chips are made in Taiwan, right, at TSMC, or maybe a little bit at Samsung, but almost all at TSMC, right? The AI revolution right now is being run by US companies primarily, and it is using US technology, designed by NVIDIA primarily, and at US data centers. But in Virginia has historically, due to the co-location of where sort of the, ARPANET, which was the predecessor of the internet, was a Department of Defense sort of program. So we still see actually a huge domination based on sort of interconnect and connections of data centers in Virginia. And, just over from 2020 to 2022, right, we saw, power use jump from around 116 terawatt hours in Virginia to about 133 terawatt hours.
Mm.
So that's like more than 15 terawatt hours in growth just in that one region alone. Almost all that is dominated by the increase in data centers. So this load growth that we're starting to see being driven by AI, it's not a hypothetical thing that we're like looking to the forward.
Right.
It is happening now.
Right.
And I think this is sort of coalescing with two other sort of macro forces that are going on, which is that through huge amounts of policy in the U.S., we are not electrifying maybe as fast as you thought we are, but we definitely are seeing increased electric vehicle power demand, power charging demand, which I think is going to continue to grow. Maybe not as fast as some people initially thought, but it definitely is happening. I think one of the things that we have to be really interested at, what could be a game changer, is the proliferation of cheap Chinese sort of electric vehicles that are being mass produced at much lower prices than the American competitors. If they start really having a significant, market share here in the United States, we could start seeing a real takeoff in electric vehicles. And we are starting to see also heat pumps really become more and more of a method of heating in the United States, particularly in the northeastern United States. That's like cities like New York City have fossil fuel bans, right? You can't build new housing with non-electric heat, with non-heat pump based heat. So we're starting to see a combination of these triple electrification, and this is really changing the world now, because for, as you were saying, for really decades in some ways, we've been watching power efficiency, right, really keep load growth stable even as actual economic activity dramatically increases. And we don't have to look, we can just look around this room to see that change. If you look at what a television once was with a cathode ray tube based TV, but when we replaced that with LCD and flat screens, we really reduced the power use of that dramatically. Lighting has gone through a revolution with the proliferation of light emitting diode based, LED based lighting. Now we've sort of had all those efficiency gains sort of now baked in. And now we're seeing on the electric power side just multiple drivers of electric power use that in some cases are enabled by large amounts of government policy, and in the case of AI, just straight commercial demand. And that is causing, for the first time, I think, in a really long time, utilities are trying to figure out, and maybe in some cases struggling, how they're going to meet load in a lot of regions. And that's a very big difference than where we were 30 years ago or 20 years ago, or even in the first nuclear renaissance, where load still was relatively flat in terms of load growth.
Right. I mean, one could say that certainly not an absolute decoupling, but there's been a partial decoupling of economic growth from electricity use. There's been a certain amount of, I'm sure, a Jevons paradox there, and maybe that's covered over in terms of the flat demand by the offshoring of a lot of heavy industry, which I understand used to be a pretty big source of load growth. And certainly globally, power use is increasing. I think partially, obviously, because of the economic development moving at a breakneck speed in China and India, for example. Power demand globally has been going up, but you're right. I mean, this has been this flattening. I'm thinking a lot
And
about.
we should be clear, like, it's a flattening of maybe electric power use, right?
Yes.
And even if we talk about total energy, most energy still is not consumed as in the form and its end use as electricity.
Right.
What's going on in the electrification sort of revolution that may or may not be happening? Yeah, but it definitely is. We are seeing more and more, particularly on space heating and water heating, which is a large portion of, say, residential energy use. Historically has not been in the United States really electrical. I think, like, for space heating, it's less than, like, more than 90% of space heating has historically been non-electrical in nature, in terms of, like, BTUs, and now that's transitioning more and more as heat pumps start dropping in price, and as they're encouraged, we're electrifying that. So even though total energy demand might be going down or might be stable, the electricity share of that pie is growing and growing.
Right.
Ideally.
I'm thinking a little bit about the soft path from Amory Lovins, the idea of negawatts. And really, some of his ideas went against the concept of electrification because that's inefficient. Certainly, in terms of thermal power generation, from pure thermodynamics perspective, you're losing 60, sometimes even 70% of the energy that's put in. And I'm thinking about places which have been conducive to electrification so far, and those are places I think that have really followed a hard path. And I think about Quebec with its massive investments in its hydroelectric infrastructure, its ability to export. I mean, up until recently, with the droughts that have really impacted the basins for these hydroelectric facilities, a surplus of power, and certainly the northeast states in the U.S. really starting to depend more and more on that for clean energy. But are we going to be experiencing a return to more of a kind of hard power path, or I don't say soft path, hard path, in terms of not only it being difficult but needing to have hard power to?
Yeah. So we should be clear a couple things, right? One, the thermodynamic thing that you just talked about, that's of comparing heat to work or heat to. And remember, just most heat can't be converted. I mean, unless you're at a really high temperature heat source, can't be converted to useful work. So, like, one of the things that's cool about electricity, like if you think about mechanical work, like you lose at a nuclear power plant, you're losing, 66%, or slightly more of the heat is being wasted, quote unquote. But you can't really actually ever convert that heat into useful work just because of the second law and just general practical efficiency. Internal combustion engines 20 to 30%. But what is cool is that the turbine is making that into mechanical work, and you lose only a very little amount in the actual generator side of things, right? The actual conversion of mechanical work to electrical power and then back is pretty efficient. So I think electrification does make a lot of sense for thermodynamics. The edge cases on heating, we're not talking about work, we're just talking about thermal stuff. But that's what, of course, a heat pump is enabling, is it's not able to pump heat against the thermal gradient. And therefore, you can get a coefficient of performance depending on of 3 or 4, meaning that for every 1 watt of electricity you're putting in, you're getting 4 watts or 3 watts of heat back,
right?
Which is great. I'm not sure it's I don't think there's ever a soft path that would have ever happened.
Right.
I don't think that people were really ever willing to. I have never seen people ever really willing to change their lives in a meaningful way to reduce carbon emissions.
Right.
And like my example of this always was 2020, right? We saw during the COVID lockdowns, right, which were devastating and had huge amounts of social implication, were miserable to almost anyone who obeyed by them. And total global carbon emissions dropped by less than 5%. Right. And that was like way beyond what we'll ever have social license to do. We are not going to be able to do a soft path to decarbonization.
What is referring to in the soft path is some of Amory's ideas, again, about because of that.
I don't really know Amory's stuff.
Yeah, that thermal inefficiency was like, we should do more sort of small is beautiful, localized. And maybe we should just have coal burners in apartment buildings to provide heat. That's more efficient. Anyway, I don't want to get too sidetracked.
Yeah, sorry, we got sidetracked of the AI discussion.
Yeah.
What I'm going to say is, I think this is short TLDR is this is a very good secular trend for nuclear power, and maybe even for the general sort of clean energy revolution, I would say, that we need, that people can debate about.
Right.
But this is driving actual growth, and that growth can hypothetically be used to power further decarbonization, if we want to call it, or it could not be. Right. And that's the real question that we have to ask here, is that what's going on? I don't think there's any world in which we want the power to go out.
Right.
And so the real question is going to be, if the AI revolution and this electrification revolution that we're seeing happening, is it going to increase carbon emissions dramatically, or are we going to be able to, through policy and through the economy, actually drive this to real sort of decarbonization and further out clean energy infrastructure? That's the question.
Yeah, and again, I think I'm a bit of a cynic on the side of I don't really see climate leading to. I mean, certainly it's leading to a lot of investment in renewable energy. We've added capacity and we have brought emissions down. I think modestly in a number of areas through fuel sparing mostly. But in terms of certainly as a motivator to build nuclear, I find it insufficient because of just how hard nuclear is. People build nuclear for really pragmatic reasons, primarily, I think, over its history for energy security reasons. But I do find that simply the dollars and cents of it. These big tech companies are filthy rich. The kind of valuations of TikTok, for instance, I think it was like 9 or 10 billion, and all LNG exports from the US were like 23 billion. That was just a recent stat I came across. And it's just the energetics, like energy is required to power servers that make TikTok possible. We've got some weird valuations, but all that to say, the tech companies have shit tons of money. And if we're competing for, creating power for particularly hard to decarbonize sectors, versus, building the data farms, which, powerful people in this country and our societies want, I see one trumping the other in terms of the implications. But I'm willing to be proven wrong.
So I'm not sure. We don't know yet. I mean,
Right.
it's just happening. I think the companies, at least hypothetically, have hard clean energy targets. And, historically, these companies have done renewable energy credits, right? But we are starting to see them matching for 24/7 clean power, right?
Mm-hmm.
And the question, and we are seeing this in the Susquehanna deal, and I bet you Meta and Google and Microsoft are not far behind, but who are buying power from nuclear power plants, right? Because the nuclear power plant, of course, as I think this audience would know, is a really good source of 24/7, highly reliable baseload generation that could power something like a data center. And going back to the AI sort of thing, one of the more interesting things that we've been learning about at my company about what's going on in the AI revolution is that we generally think of the power load, the highest compute load is going to be in what we call training the the large language models that actually make up, GPT-4 or the other models or what's Google's model. I'm blanking on its name, the one that just got in all the trouble. But that training takes a huge amount of energy to do, and that training can really be what we're doing in training. Just so that people know, is that we're basically making the model weights that are necessary to actually build these large neural networks that power these large language models. And that's historically been a driver of much of the power use that we're seeing out of these AI, out of the amount of energy that excuse me, that AI is taking. What's happening though now is, so if you think about how you do an AI model, it's like an LLM. You're going to generally have inference, which is when you're querying GPT-4, right? That's like, like write me a song about, nuclear power. And then it makes, some corny ass song about nuclear power. But then the actual training is the actual building of that, the ingesting of that massive corpus of data to make that, to teach that LLM how to do that. What's happening is, as we're starting to see the dramatic increase in the utilization of large language models and other AI systems, we're starting to see that even though the amount per query is much less for inference-based tasks, because there's so many queries that are coming up that we're starting to equalize the amount of energy use from training versus inference. And the thing about inference is, if you talk to a large data center EPC, what they'll tell you is that they need to have, these companies are targeting a couple of milliseconds for the quality of surface, for the latency between when a user queries a AI-based data center and when it responds. And that limits where those data centers can be located by the speed of light. So if you think about a 5 millisecond or 2 millisecond QoS target, which is one of the more ambitious, upper targets of what we're seeing, that means that it has to be in a couple 100 kilometers from where the user is, just because you can't actually communicate faster than the speed of light. Wow. Now, one of the things we don't really exactly understand is a couple of milliseconds is pretty imperceptible. We're not exactly sure what the future applications of AI that people are envisioning that are causing these requirements, but this is causing for a pretty big. So training you could train halfway across the world, right? And transport the model weights over a couple hours, and you spin up a new data center and spin up a new node that's running this model. But in terms of actually doing inference, we are starting to see the need for it to be co-localized or closely localized to where the actual user is.
Wow.
And this is also going to be happening as we start seeing more multimodal AI models that are not just generating text, but sound and video.
Yeah.
And it's just like a CDN, right? We generally have CDN edge servers close to where the content distribution network, to where the user base is, which means that we're having a double challenge now.
Right.
Not only is it a huge amount of energy consumption, but we have to localize it more than we would normally think we would have to.
And this is totally fascinating and new to me. I did not understand this localization requirement, and it seems ridiculous for milliseconds.
I think it has that's what they're targeting,
right?
And I think it has to do with what they're imagining AI is going to be doing in a couple of years.
Sure.
Or
because
6 months.
you think about energy-intensive industries like aluminum smelters,
right?
They co-locate next to big hydro dams. I mean, or big coal plants sometimes. Iceland, for instance, I've heard had a lot of server farm growth because of its abundant baseload generation due to geothermal, but mostly hydro. And I think I remember you actually saying this. One of the big rationales for nuclear in the early days was you can put it anywhere.
Right.
I mean, if you have a water source, let me say that. I mean, there's air cooling and things like that, but it's much more flexible, and you don't need a rail line shipping in massive amounts of coal, for instance, or you don't require the massive hydroelectric resources.
Exactly.
So again, this is another reason why nuclear seems to be an interesting match. And I mean, again, from like an ethical, moral perspective, I am really concerned, and we're going to get to this, I guess, from a values perspective. If we're feeling a squeeze on demand growth and on power, and that leads to higher prices, who loses out? And who does the power go to? The tech billionaires and their interests, or ma and pa? But that's actually a sidetrack. I don't want to get there. Let's talk a little bit about this Susquehanna deal. This is the co-location of a server farm, I think presently 160 megawatts, planning to go up to 960. A lot of criticism, because I think Jesse Jenkins, for instance, and other commentators are saying this actually isn't doing anything for climate change. It's just adding a baseload demand. And a lot of people are saying also they're applying, I think, additionality.
There is no additionality, is what they're saying.
So yeah.
Right? And that's right. I mean, just plan out, like that plant was running, it runs at, 96% capacity factor on average, right? It's a really great performer. I gotta get at a refueling year, it goes out to 88% capacity factor, because it's it's a two big boiling water reactors in Luzerne County, Pennsylvania, on the Susquehanna River, of course. And the idea is that plant has been operating for decades, and it's serving load right now. Mm-hmm. And if you just add a new load without any new capacity, that's not really doing anything from a climate change. I've heard some nuclear advocates say, well, this will make sure that the plant keeps online. Now, on the other hand, we have the Inflation Reduction Act, which is already giving a production tax credit to nuclear generating stations. I don't, till at least 2032. I don't think Susquehanna was ever going to go out of business. And we already are hearing talks about, 3 Mile Island Unit Number 1 being reactivated. We're obviously seeing Palisades already being in the process of being reactivated. And I think the Biden administration, to their credit, is really trying as hard as possible to get the plants that we have brought back, raise them from the dead. But going back, it is absolutely true that from a climate change perspective, this is net on net probably it's just a new load on the grid,
and other people are going to be using dirty electricity.
Yeah, and no one else, they're not like turning off the light somewhere else to compensate for it. So it's not doing anything for climate change except increasing electricity use. And that use that Susquehanna is not serving will be served by other presumably fossil or hopefully renewable assets or something, but it's not going to do anything. Now, I have the bull's case for nuclear, though, is there's only 92 gigawatts or 93, 94 gigawatts, depending on how much we're kind of Vogel in this, right, of nuclear capacity in the United States. And that means that eventually the tech billionaires are going to run out of of nuclear power plants to co-locate their data centers at.
Yeah.
And that's a really good thing. For nuclear power, if you're in the nuclear industry.
Right.
This is what we've been looking for in some ways, because what we have is demand, and we have direct off-takers who have very deep pockets.
Right.
And who have been interested in nuclear. So I view this in the long term as a very good secular trend for nuclear that might actually be the real nuclear revolution that we've been waiting for. And if we couple this with the need to possibly make these data centers closer to the population bases. There's a lot of places in the Northeast United States, for example, that where hopefully we're not going to be able to, just ship gas up to it, because there's a huge prohibition in many of these places for building new gas pipeline capacity. Not necessarily, we can argue about the merits of that. Might not be a good thing. It might be a good thing. probably it's more mixed than I think a lot of people think. But it's certainly going to be, how are we going to make that electric power? Well, a lot of it right now could just be, using fracked gas and just pulling up a combined cycle gas turbines. And,
Right.
with gas, it's so cheap. That is what the sort of flip side of this. And you see a lot of the decarbonization advocates really getting concerned, because what's clear on so many of these ISOs and RTOs, whether it's New York, New England, PJM, they don't know,
Right.
period, end of story, how they're going to keep meet load growth. And there's gigawatts and gigawatts and gigawatts of deficit right now on these grids, based on, even before the AI boom, that this is only exacerbating this. And so secularly, for society, it's not going to be a great thing. But if we're looking for an actual need to have nuclear, this is the best environment that we've been in a couple decades.
I hear that a lot. That, again, because of this increasing demand, like nothing is better for nuclear than demand projections that are going up and up and up. You need customers for kilowatt hours out of highly capital intensive projects. If you're going to put down 10 billion for a gigawatt, you want to be damn sure there's going to be customers at the back end of that. And now it looks like that demand is emerging, and PPAs. I think Microsoft announced a PPA of $115 per megawatt hour. That's going to incentivize a lot of building of nuclear. And I guess this gives maybe the nuclear industry a chance to dust itself off and maybe follow some of the recommendations that the decouple has been making. But it's interesting, as you were saying, the demand is coming so fast. Gas can be built far quicker. Do you think nuclear can catch up, or are we just going to have AI cannibalizing existing nuclear power,
and then gas
filling in the gap? Or is gas going to be a transition fuel to nuclear getting its act together and being able to build up for that demand, in the 2030s and 2040s?
Well, so here's I think the challenge is that nuclear projects, I mean, it's always the same challenge. It's can we deploy nuclear fast enough so that a data center is being built? And these data centers, we're building gigawatt scale data centers.
Yeah.
And the other flip thing is that dozens of states at this point have banned new data centers because they don't feel like they have the power capacity to actually meet them.
And they don't bring any jobs.
They bring few jobs, okay. Right? Yeah.
Like how many? How many?
Very, very tiny.
Like dozens, maybe?
Like dozens.
Right.
Yeah. I mean, security, and then you have people, nerds come in occasionally to fix things and stuff like that. There's some technicians.
Essentially jobless.
And they just suck huge amounts of power.
Right.
So and they just don't have the power. So the question that if the nuclear industry wants to reach this moment, it needs to be able to prove that it can actually meet that demand in a reasonable enough timescale. Otherwise, gas plus maybe renewables, but in a lot of these areas, you're not going to even be able to deploy renewables because of siting issues, right? So the question that we are facing is, can the industry get a sensible plan together to be able to deliver fast enough to meet this demand growth? And this brings us to, I think, what the big sort of debate that's going on is that a lot of places, like Microsoft in particular, are thinking that microreactors are going to be the pathway that they're going to take to basically, power their new data centers.
This has been a interesting trend over the years. I've tended to lean on the side of large reactors, basically because I've sort of repeated this ad nauseum, but I'm a defensive pessimist. I think everything's going to go wrong. Get surprised when it does go right, but it makes me very conservative. It makes me try and investigate, what are the unique circumstances under which nuclear has really deployed itself quickly and economically. And I've tend to be brought back to that bias. I'm certainly someone who holds strong opinions loosely held. But it has been interesting because I've had people push back and say, listen, like the United States, and this was as recently as maybe 3 years ago, 2 years ago, utilities in the United States are never going to deploy gigawatt scale nuclear ever again. So we need to modify. You should stop advocating for this. And I go, well, you will concede that the economics of large are better than small. Yes, but it's just not going to happen. No one's going to take the financial risk, or maybe the demand won't emerge. And I was always saying, well, I'm going to kind of, hold the candle on this belief. Partially out of being a climate hawk and being like, well, the demand should show up because we're trying to decarbonize. And of course, that's been a little stunted. But anyway, here we are. I've kept the faith for a few years, and it's just interesting to see that. But let's talk about SMR, micro reactors, and what these gigawatt scale server farms individually and just the collective demand of all that infrastructure, does that tip or change the balance of, what makes the most sense to build?
So I think the question that we're going to have, and I think the SMR, I think sort of SMRs are going to be now in the same camp as the large light water reactors at this point. At least the SMRs that we've been talking about, as we've talked about in this podcast. The problem is the SMRs right now are taking the exact same amount of not the exact same, but actually proportionally more civil works, more concrete per megawatt than a large plant is. And the problem is that these civil works are not things that are easy to have learning curves, and still we're going to require large workforces to agglomerate onto a site. And the classical edge case that you get into with an SMR advocate is say, well, a lot of places can't take a gigawatt or 2 gigawatts or 3 gigawatts of new capacity. Now the whole issue is that we're building gigawatt scale offtake right at the site. So it's becoming a less compelling argument considering the civil works that we're seeing. And I think as the BWRX 300, which is the GE Hitachi's 300 megawatt boiling water reactor SMR, what we're seeing out of that design is that these are very, it's not a factory manufactured module that's being put into a pole barn. It's being put into a massive subterranean, structure that's, more than 30 meters in diameter and more than 20 to 30, more than 20 meters deep now, even more deep than that subsurface, with a lot of steel concrete composites. And what the nuclear engineering experts I speak to are increasingly concerned about the intensities of civil works. We would also say that NuScale kind of died because of the civil works, right? While the actual NuScale power module, of course, is transportable and factory fabricated, that massive common reactor building is larger than the nuclear island of an AP1000. You get half the power out of it. So in terms of project length and timeline, considering it's going to be more labor hours per megawatt electrical, more concrete, more steel per megawatt electrical, I'm less and less able to see the case for these SMRs for meeting this sort of demand. Now, the other side of that pendulum is the microreactors. And the idea of the microreactors is, oh no, we're actually going to make the reactors so small, 50 megawatts electrical or less, that we don't actually need that much civil works on the site. Like it really is mostly the factory fabricated module, and maybe it's sat on some sort of cocoon or shell that you're putting the reactor.
If you have to build like 50 cocoons or shells, doesn't that start to add up in terms of civil works?
But it could be, you could imagine a world in which it's actually but you could deploy it much quicker, right? It's just much simpler to do a basic, concrete base mat that's very tiny, that comes in, a couple of factory fabricated prefab module, or even precast concrete that you're transplanting from a factory and placing it all on thing.
Gotcha.
The problem, I think, is that these economies of scale with microreactors you're really tiny then, and you're really having a hard time getting the economies of scale to work. And I think of it, just some of the basic core physics of neutron economy becomes very, very challenging as you get to these very tiny reactors. And if you look at, say, the Westinghouse eVinci reactor, and if you try to find burnup numbers, that is, burnup relates to, in nuclear engineering, it's the amount per kilogram of fuel, and that's the enriched uranium, kilogram heavy metal we call it, how much thermal energy in megawatt days or gigawatt days you get out. Problem is that because these cores are so tiny, it looks like Westinghouse hasn't published a number, but researchers at Brookhaven National Lab did their own neutronics analysis and tried to calculate this. Just from the basic core physics, you really lose on just fuel utilization. And when we think about nuclear power, we don't think that fuel is a general driver. But what the numbers at BNL are showing on the edge case, we're going to be using 16 times more uranium metal per unit megawatt than a light water reactor.
We're a little short on LEU, not to mention a high assay.
But it's even more profound than that, because it's not only just the uranium ore, which is also, we're seeing increased market pressure for more uranium ore. Then we're also seeing in the whole front end of the fuel cycle, we're seeing tightness in enrichment, in conversion, in deconversion. But then the other problem is that all of these, microreactors, the way they get around having a full containment building is by using what's called a functional containment, which is generally by using the fuel type, is something like triso, like uranium oxycarbide, tri-structural isotopic fuel. And that is a really expensive fuel to make right now.
Mhm.
It's costing about $10,000 a kilogram right now to fabricate trizo fuel. And we're utilizing it a lot less efficiently. We're utilizing a lot more uranium. All of a sudden, it's becoming more and more challenging to figure out how do we actually get the economics of a microreactor to work, not to mention the capital cost issues that we're having from lack of economies of scale.
So I think I got the stat from you regarding the Evinci microreactor requiring 900 kilos of HALEU, which incidentally is what Centrus committed to making with this, I think, expanded, was it, excuse me, 16
16
centrifuge cascade. In the end, they didn't even meet that goal, I understand.
Well, that's only because of admittedly, that's not their fault. It was because the Department of Energy couldn't provide them uranium hexafluoride.
Ultimately, the goal was not met. No, I'm not slamming Centrus here.
It will be.
But what you're saying is that 900 kgs might be an underestimate, given these poor neutronics and the lack of a published number from Westinghouse. And
some people are estimating it's in the tons of HALEU per 15 megawatt or 5 megawatt electrical reactor. Microreactor, and that's going to be the ultimate question. I think that's going to play out in the next couple of years. I think you probably know where my biases are, what I think is going to win. But the real question is if there actually is a microreactor that can be sort of factory deployed, sited, and set in a couple months, that's going to be incredibly attractive to doing this. The question is, can we make it economical? And when
it's attractive for a small server farm, but a gigawatt server farm, just do the math. I mean, that's a lot of microreactors.
It's going to be hundreds of microreactors per plant.
Are you convinced by that? Does that sound economic?
Well, once again, if it turns out that actually these things, I just don't. The first question I have is the fuel, and how do you get over this? The basic neutronics of having a tiny, because neutron economy. What we're talking about is how many. In a nuclear reactor, as we know, you split an atom, and that atom releases neutrons. And those neutrons don't have a GPS that tells it, oh, this is where the next fissile atom is.
Right.
It sort of is taking a drunken walk, and it might hit another fissile 235 or 239 nuclei and split that. But it might also get absorbed by something else, maybe by water or maybe by some of the elements of the fuel. Or it might leak out of the core.
And activate something.
Well, or hopefully not, and hopefully just be absorbed into water or something and shielding, right? But the problem is that as you think about it's just geometry, right? If you think about the surface area to volume of generally we are cylindrical, right? A big core is going to have the probability that a neutron in the middle of it is just going to leak out of the core. It's pretty low. It's going to hit something before it leaks out. The problem is when you get very, very tiny, you're leaking a bunch of neutrons out of the walls of the reactor core, the boundaries essentially of it. You can put a reflector around it that bounces them back, but no reflector is going to be that good. So there's just an inherent neutronic disadvantage of going that tiny from fuel utilization. And so what I'm trying to say is the laws of physics are the laws of physics. And unless fuel is going to come much, much cheaper than it already is, we're going to have a pretty hard time getting the economics to work. And that's ignoring all the other drivers. We don't generally think of fuel as a major driver of the cost of nuclear power plants. But all of a sudden, when you 10 times the amount of fuel or 16 times the amount of fuel, all of a sudden that becomes a little bit more significant. But now we're talking about also all the capital costs associated with building 5 or 10 or 15 or 20 megawatt electrical reactors over and over again.
So, there was a much maligned article by the nuclear community. Alison McFarland was one of the principal authors, and they talked about, the waste volume that was created. And I think a lot of nuclear advocates said, yeah, maybe, although exaggerated and picking, worst case scenarios. And, a lot of the advanced companies in particular were saying, listen, you didn't consult us. We had better numbers for you. But it sounds like you will make more nuclear waste. I'm not afraid of that waste. But with how we currently manage waste and the plans of doing things like deep geologic repositories, which in the Canadian example are going to be north of $20 billion, if we're going to manage it that way, the volumes might matter. Or
I don't know.
No.
I mean, I just don't think about nuclear waste. And maybe that's my own pro-nuclear, nuke-pro bias.
But I mean, again, it's $20 billion for DGR.
I don't know, just procrastinate and put them in casks. I don't know. Sure. I just don't want to even think about it.
Okay.
Yes, I mean, I haven't done the economics. I imagine that there is an economic case that this is a problem, but that is not what I'm particularly worried
Sure,
about. I really am not, and I just like, maybe that's my own biases. I just like am kind of saying, we can safely store nuclear
Right.
waste pretty cheaply.
I'm just to clarify,
High-level
the only
waste.
reason I'm worried about increased waste volume is just if we're crazy enough to handle it the way it's being planned with DGRs, which cost tens of billions of dollars, then that starts to matter to me. Not the sort of danger from the waste and our ability to manage it on an intermediate basis. Okay, I want to get controversial on the Canadian side. So we have this plan at Darlington to build 4 BWRX 300s. And again, to me, this is like a path dependency from a time where we really didn't see demand kicking off, and it might have been foolish, and we might not be able to finance a gigawatt scale reactor or a series. The site is licensed for 4,800 megawatts. We are treading water by taking Pickering A offline. Luckily, we succeeded in saving Pickering B. But the addition of 1,200 megawatts, we're treading water. We're not adding capacity. We're relying on Bruce to start building additional nuclear capacity.
Bruce
and frankly,
C.
Bruce C. But frankly, that's not a lot compared to the pathways to decarbonization projections of 18 gigawatts, and probably what I think is actually more pragmatic rationale for deploying, maybe setting a whole bunch of data centers. And so the X300, as you're saying, I mean, it brands itself as nth of a kind, but this plant architecture is certainly first of a kind. That's pretty novel. There's some unforeseen risks there. But fundamentally, and the rationale is to build it in order to be able to deploy, in smaller provinces. And to me, that's a noble goal. I personally think it should be a federal government responsibility if you want to have a nuclear strategy that's deploying out of province, not a provincial utility. I'm going to get in shit for saying some of this stuff, but and maybe you won't reply, and that's totally fine. But to me, it's like there's a new rationale now to do large at Darlington. You have these data centers, and also, contrary to what all the anti-nukes are telling us, that we could, shut our nuclear fleet down and go efficiency and bring water in from Quebec. Quebec is hurting. We've been burning gas all year to export to them so they can hold back water in the reservoirs for winter. Luckily, it was a mild winter, but they lost $1 billion in exports in Quebec. So, I mean, if we produce big power at Darlington, if we consume the 4,800 megawatts on nuclear sites, which are very hard to come by, now I think there's this security. Are the PPAs secure enough? Are they kind of 5-10-year PPA might make a nuclear developer a bit hesitant? How locked in are these PPAs? How much of an economic rationale is there in terms of de-risking large nuclear at a site, we'll just say like Darlington, so you don't have to wade into the politics?
Yeah, no, I think we've been instructed by certain members of the Canadian nuclear community not to comment about, God forbid, members of the public comment, and maybe that was more directed at you than me. But I think without talking about, so here's a couple of things that are good. One is that what are good about a lot of northeastern nuclear, I guess it's southeastern Canada, but northeastern United States, southeast, like Ontario, Quebec, New England, New York, Pennsylvania. What's good about these places are they're wet places in the world. Like, we were just at Bruce on Lake Huron. Lake Huron's really, really big.
Yeah.
Like, there's no way we're going to have to worry about consumptive water consumption. And one of the things that we also are doing at data centers is cooling, right? All of this thermal load that we're putting into the CPUs and GPU, they basically all get converted into heat. As I said, the actual amount of thermodynamic computation that you're doing is very, very little. So almost all of it's just lost in resistive load on the heat. So when you put 700 watts into an H100, right, which is an NVIDIA GPU, a Hopper microarchitecture, right, that's almost all coming back as heat, right? That needs to be taken away. And so one of the good things that we're looking at nuclear sites is that they're generally also co-located with large cooling water resources. Mm-hmm. So we're really seeing this nuclear marriage between nuclear and data centers work for a bunch of reasons. The siting is really good. We have that direct power. We can just take off the bus bar. And then also we offer generally co-located on Lake Huron or Lake Ontario to bring up Darlington and Bruce, right, which is great for that. And we are starting to see with Hydro-Quebec, right, in this region of the United States and of Canada, right? I live in New York State, and we were relying a lot on the Quebecois to basically export power down through Chippy and other HVDC lines. And as you just said, Quebec right now is importing power from Ontario because, I mean, there's a combination of things, but I think there's also, Quebec has always had a large amount of electrified heat, but we are generally starting to see that electric power use is also increasing as well. And so we are in this space where it's, we're going to need a lot more power. And the question, I'm not going to opine on it, that if I'm OPG, I would be asking at the Darlington site, if I have 4,800 megawatts electrical sited, licensed, or have an impact statement for that, does it make sense to use that site for what, 1,200 megawatts?
Right.
Or are we going into a world where we can be confident enough secularly
Right.
that there's going to be enough demand for low carbon power that you might as well take that site and build, 4 AP1000s or Monarchs or APR 1400s or ABWRs that, of course, won't opine on the NSSS selection for it. Of course I will. But that's the question. And it's a real different game. This is a game changer if this holds. If this pattern holds, we are looking at where there's a premium for gigawatts and gigawatts and gigawatt hours of low carbon firm electricity, and we don't have that much supply coming onto the market, which really goes back. Does it make sense to build 4 BWRX 300s there?
I mean, I think there's, again, path dependencies and sort of sunk cost fallacies that play into these decisions. The SMR paradigm, again, SMRs in grids where you can't, deploy a big reactor because it's more than 10% of the grid. And if it has an outage unplanned, it's a big deal to compensate for. That's an absolute case for SMRs. And we have a number of provinces in the country that really don't have hydro and require SMRs to decarbonize. I don't think they're going to be as economic as large, but if we're willing to pay a cost premium, if the federal government's willing to step in and backstop that and support, that for climate reasons, I think that's fabulous. For me, like the bull's case for nuclear in Canada, accepting that, I think is a pretty obvious premise that nuclear power has tended to scale up in terms of chasing economics, is, building big nukes in Ontario, in Quebec, and in BC. And if the Quebecers won't do it, why don't we build them close to the Quebec border and strengthen our transmission lines and, or paradoxically use the existing lines to be sending power back to them if their power demands are dropping. But we're kind of veering off of AI.
Well, the question though is that I think for AI, right? Going back is that these are great sites. Canada's cold, as we know. It's cold. It's got a lot of water. Right, it's great for doing passive cooling and getting that power utilization efficiency really, really low.
Not having to build cooling towers.
It's
expensive,
hypothetically, right? Although, yeah, and even if you do have to build cooling towers, it's so much easier to have so much makeup water for the evaporative losses and for the blowdown of your cooling tower that these are great sites. Toronto is a megapolis. Right, the Northeast has Boston and New York City, etc. We really are in this place where this corner of the United States and Canada has a combination of high populations, relatively good economies, going to be a real AI load center, and they don't have a clear path to make that cheap power, except for the long history of nuclear power in these regions. So I'm seeing for the northern part of the United States, particularly in the eastern side, there's really going to be an opportunity, and in Ontario, for new nuclear. And I think that is going to be the sort of paradigm shift that we all have to embrace, which is a good one, which is that maybe we're going to be supply constrained, not demand constrained.
Right.
And that's the greatest thing that we've ever had for nuclear. Because the one thing that happened, I think, in the noughties, to use your term, in the first Renaissance, is we had a combination of increased efficiency, decreasing electric power, decreasing natural gas prices, and we had decreased electric power demand, especially as the global financial crisis hit, because economic activity sort of decreased, and so we just didn't see, if not decreases, we didn't see almost any load growth, and it became harder and harder to justify such a large capital investment to build new load, even if and people didn't value carbon that much and probably don't do it now. But now we're in a situation where the real question I have to ask is, are we going to be building gas, or are we going to be building new nuclear capacity? And the answer is probably both, right? Plus renewables to serve this increased AI demand. And the real question that is can the nuclear industry present a credible enough path so it's not just Susquehanna 1 and 2, it's building Susquehanna 3, Bell Bend, right? That question about, can we actually get a strong enough demand signal and have, as a counterparty, if you're Microsoft, Google, or Amazon, can you actually have as a counterparty a nuclear provider that can actually that they can be confident that they're going to have power to power their data center in by the time it's done.
It's interesting you talking about Susquehanna 3. People talk about Vogtle 5. I mean, Vogel's maybe an exception because there's now 4 reactors on it. I think it's the largest single nuclear site in the U.S. But in Canada and Ontario, we filled out our sites, right? I mean, you were just at a 4 reactor station on a 8 reactor site. There's room at Bruce. It's a huge site. But we are a little bit constrained now in terms of Darlington. Apparently, if you do the 4 SMRs, there's not really room, certainly not without opening up an environmental assessment process, which will take
Is
forever.
the surrounding of Darlington, is it like...
It's not a huge site, Darlington B.
But I mean,
in
like,
terms of lakefront, right? And then we have Nanticoke, which is an old coal site. We have Westleyville. Like Ontario Hydro, back in the 60s and 70s, started looking and planning out and acquiring properties that were favorable for basically large coal or nuclear plants. And they built some nuclear plants on them, and they built some coal plants on others. And there's a couple empty sites, well, maybe only one, Westleyville. But in any case, we're potentially running out of nuclear sites. And in the U.S., you have a lot of single or double station plants.
Yeah.
You can add a ton of nuclear without having to go through all of the issues with permitting and the social license around a new site. Like it sounds, not to mention the sort of brownfield coal sites.
Right.
It sounds like there's a lot of places to build.
And you're saying there's not a lot of places to... I just had Bruce, and I just like, this place could have 30 reactors.
Right.
Like if you think about the water, the lake frontage, you don't have to have the reactors on the lakefront.
Right.
You just need to have the makeup. You have to have the circulating water intake and outflows.
Yeah.
Right. And so you can basically pipe in the water, 500 to 1,000 feet inland.
Right.
Right. If you have a big enough pipeline. Right. If you think about like a nuclear plant like Seabrook.
Yeah.
Right. Seabrook is not in New Hampshire. Right. Seabrook has a once, an open cycle once through. Takes seawater in and squirts it back out through a deep, long outfall. But that's like, Seabrook is not on the beach.
Yeah.
Right?
Yeah,
it's like in a marsh, but there's a big underground 16-foot diameter tunnel.
All I know is that there's preoccupations around not having enough sites or making sure we preserve sites because there's competitions for these sites. Farmers want to farm them. Housing developers want to develop them. Manufacturers, real estate's...
so maybe this is something where regulatory reform really is important. And I think one of the things that we do need, I'm one to always not defend the NRC, defend the regulators.
Right.
And I don't know the Canadian system because I just, it was only until I just drove up today that I figured out that it's not, you guys have your own government and own laws. not the United States. I just thought it was the 51st state. But one of the things that is going to be a major problem in the United States regulatory environment for deploying nuclear as fast as we're going to need to do to meet this demand is going to be not necessarily on the nuclear side of regulation. I think we could speed that up pretty quickly in some ways. There's some statutory changes that we need to have for the mandatory hearings to be abolished, but especially now that we have such a amount of certified designs, we know how to cite those designs, do the geotechnical boring and seismic analysis that's needed to cite it. The big problem is the environmental impact statements. Right. Which are historically the rate limiting, the slowest part of the nuclear for the Part 52 process. It's getting those EISs issued. And that's not in nuclear legislation in the United States. It's the National Environmental Policy Act in the late
NEPA,
60s, NEPA. And the question that I have to ask that we're going to have to, I think nuclear advocates are going to have to do is, how do we get the NEPA reform for EISs for environmental impact statements to be issued fast enough that we can really actually start building nuclear quickly enough? And that's what I think we as advocates are going to need. Then the entire community is going to have to razor focus down on how do we get EISs issued fast enough to be able to enable nuclear to be deployed. On the industry side, we need to start seeing a real battle plan being put together about how, if we go the large light water reactor route, how do we get ABWR level, build times of 48 months and below for a large light water reactor to be put together. And so we do have a regulatory issue because it's not just previously it was like, well, when you're doing the EIS, you don't have a construction site going, your capital costs or interest costs are low, right? Because you're not actually building the plant until you have the EIS. But now if we're talking about, we actually need to meet load quickly, we need to actually just think about the total schedule time from I decide to build a nuclear plant to nuclear plant coming online. Every bit of time needs to be compressed. Yeah. We got to figure that out. And there is real regulatory barriers to getting this deployed quickly.
Okay, which I think is going to move nicely into AI applications because I've got a couple ideas here. No. I think you'll find this actually interesting. So Sam Altman talking about needing a energy revolution. And of course,
it's going to be Oklo.
Silicon Bro is going straight to fusion, and then
and Oklo.
Okay, pretty small reactor. That being said, this is classic, right? When the nuclear industry starts talking about innovation, they innovate the stuff that probably doesn't matter, the NSSS. From Jacopo's work, from MIT work, we know that the majority of the plant costs in terms of overnight construction costs is actually boring old stuff like balance of plant, civil works, etc. So, and fundamentally, that's a question of project management. We were just up at Bruce meeting some of the most competent project managers in certainly the Northwestern Hemisphere, probably the Western Hemisphere. Really, really amazing crew up there. Exciting to see the way in which steady, project after project, refurbishment after refurbishment is training up and dialing in those human factors. Is there a role, contrary to just this idea of maybe AI cracking cold fusion or something like that, which I'm skeptical of? What about AI easing and assisting with project management? Is there a role for that?
Of course.
Do you see that as...
I mean, AI is going to be transformational in almost every aspect of the economy. And of course, AI is going to help here. I'm not so sure that's going to be we can't just, we need to be AI enabled, and we need to have developer organizations that are focusing on it. But you were just at Bruce. We just were at the sort of outage control center, right, that was doing on the MCR control center. And, there's this is a lot of real human labor issues, right? We were just talking about at Bruce, the shortage of housing right now in that area, because there's so much, because the nuclear is giving so much blue collar labor, so many jobs, right? How we do project management is AI can help. I don't think AI is going to, be a panacea for this. And what I would just say is, we know that the Japanese ABWR projects, there was no neural networks powering that. There were Palm pilots and a lot of software that was being developed. But if you look at some of the more successful nuclear projects in the United States, that was even before that, a lot of times there was computer-based scheduling and work package management, but in some cases it was taking weeks to run those computer programs, because the mainframe may have been at a Basco or at Bechtel's headquarters, and you literally had time for the punch cards to get up to from the site to the spot. So I think it's going to be helping. I don't think it's going to be transformational. I think we do need to focus on what Bruce and what the amazing team at Bruce Power and at some other organizations has been doing, which is really getting that secret sauce of how do we do this project management on these, crazy ass complicated can-do refurbishments, right down to an actual science. And that, I think, is where we're going to need to, if large light water reactors can meet this demand.
Right.
And the question that everyone's going to ask is, do we just want to totally eliminate that away and put most of it in a factory,
right,
and do the microreactor route, and fuck it, we'll just have to mine a lot more uranium.
Right. Or, this was kind of news to me, because modularity has been this buzzword. It's really sort of been associated psychically with small modular reactors in particular. But I was watching some videos of ABWR construction in Japan and seeing how modular they were through talking with you, understanding, CA70, which is 20, which is made up of 72 submodules. 72 submodules, the module assembly plant that was built in Vogel. We've talked about the applications for AI in project management. What about the applications of AI and robotic labor replacing, that stick-built construction labor, which is craft labor, which seems very hard to roboticize? But if you have a module construction factory, it would seem that that's a more compact space in which maybe you could replace some of that craft labor. I don't as a kind of, bleeding heart, I'm not sure if I'm a socialist anymore, but that's kind of the school I come from. I love the human story of nuclear. I love the human flourishing that comes along with the incredible skill set that's required. Again, I'm very kind of AI hesitant, but just to, explore this through, not to make a value judgment. What do you think about sort of, again, we're looking at AI in relation to nuclear construction productivity.
So if you looked at like that, and I imagine it's that unit which has this weird parallel between some sort of Japanese porcelain. That's the video that you were talking about.
Yeah.
It's craftsman. Yeah, craftsman. But one of the things, for example, the ABWR and the Advanced Boiling Water Reactor, the containment liner, right? They actually designed, GE Hitachi and Toshiba designed it such that and TEPCO, such that it can be done by robotic welding. right?
Yeah.
And you saw the robotic welding in the 90s. And that's not AI based. It's just literally going through a circle, right, through the diameter of the circumference, of the containment liner, and it's just doing it as robotic welding, right, using classical CNC based welding techniques. And there is going to be a lot of role for automation, but once again, I do not see, and I'm a pretty AI accelerationist. And if you look at like some of even the projections, one of the things that is going to be least impacted by AI is stuff like manual labor, like craft labor. Not because the main thing that is preventing us from doing like, robotic welding is not that we don't have we don't have computer numerical control to basically figure out how to do a weld. It's that, like, literally, if you think about what's in a nuclear plant, and we were just seeing inside CANDU and the heat transport pumps, right? Doing a lot of those welds is really hard for a robot to be able to do. You need the dexterity of a human being to be able to actually do the welding in these close sort of proximity spaces, right? So not all the welds can be automated. I think not all the electrical work is going to be able to be automated. Not all the HVAC and plumbing is going to be able to be automated. So one of the things that we do, if we're serious about,
but easier to modulate in or to roboticize in a module factory.
Yeah, so I think we're going to see a lot of roboticization in nuclear. I think that's already happened, and I'm not so sure. I think the AI revolution is going to enable that particular type of. I think a lot of that could be actually already done through the better, the robot, and there will be a robotics revolution that maybe actually is secondary to AI that maybe allows us to do a lot of this through robots rather than through humans.
Robo welder.
Yeah, but I think the question is I don't see a world in which one of the few things that I'm a pretty pessimist, AI accelerationist. I still see a large role if we're going the large reactor route for skilled trades. And I think one of the things we were just talking about it up at Bruce, obviously, there's a skilled wage shortage here in Canada and in the United States.
You just said skilled wage, and definitely some people were saying there's a skilled wage shortage, and there were some people saying
skilled trade.
Yeah.
Right, skilled trade. Sorry, I think we have both. We need to figure out a way to get and especially when we're talking the apprenticeship periods that we're talking about for welders and electricians of 4 years. It's like a bachelor's degree length of training that is necessary. We need to start thinking about the innovative ways that we're going to increase the supply of skilled labor and working with the unions and the union halls to make sure that actually we have the skilled labor workforce that maybe has atrophied over the last 30 or 40 years to be able to build these plants. Because everything that you're hearing is, one, skilled trades or shortages in all, it's not just nuclear that's being built, battery plants, electric vehicle with the Inflation Reduction Act and I don't know what the Canadian equivalent of this is. We really are seeing a return to industrialization, which is a fantastic thing. And I think, despite the almost melee and fight we created at Bruce at one point talking about what the wages are, like there is good, obviously the workers were pushing us to get it better, but people are getting paid a very decent wage with benefits, with good stuff, to being a skilled welder, a skilled electrician, a guy who's good at HVAC and doing cable trays. These are skills that are going to be needed as we move forward in this economy, and assuming robots don't take over the world. This is something that we need to figure out as an industry. How do we incentivize to build the workforce that we need? If we're talking about building 30 gigawatts or 50 gigawatts, in Canada and the US, let's figure out how do we create the labor force that can actually build those plants, because we don't have it right now.
Right. I mean, which brings me, in a more sort of broad political sense to, the ways in which our economies have become in the West kind of hollowed out from not productivity, but from the production of goods and industry towards a kind of fire economies, finance, insurance, real estate. I forget what the E is for. You think about the way that the UK, probably partially due to Thatcher, but also just kind of neoliberal globalization, a lot of the economic activity is retreated to sort of the city of London, and it's stuff that derivative trading, it's stuff that's not like related to actually building things. And it's interesting how whether everyone's been learning to code. I think we can all agree that coding is now not something that kids should be going into. They should be maybe going into the skilled trades, but there's going to be like a culture shift. I think in the US, like this could relatively elevate some of the red states or like flyover country, like where people know how to build shit. like there's a potential for this to sort of radically change things as well, in the context as well of deglobalization, or certainly friend shoring.
I
Like
think
I
this
see
is a
major societal shifts that are not just kind of AI overlords and robots killing us all Terminator style, but the ways it's going
that
to.
might help them too. But
Sure. You could okay. If you need more energy, kill off the humans, right? Especially the poor ones or whatever, and then you can use the existing nuclear fleet and run quite a few servers.
yeah, I don't know if that I don't my P doom scenarios are not that. But
Okay.
I know we don't have to go into doomerism, but in assuming that ignoring doomerism for 1 second, on the flip side, this is kind of, I think, a rebalancing that's going to be societally good.
Right.
And I'm a pessimist as well, but I think there is a world in which when we start seeing the return, and we can talk about blue state, red state, but in some ways it's urban rural.
Yes.
In some ways,
yeah.
Right, that we're talking about, and the idea that it's not going to just be consultants and coders at some 5-letter startup with no vowels. Right, like it could also be the fact that we're also giving jobs to the men and women graduating high school. They don't have to necessarily go to a college, but be paid to learn in an apprenticeship, and really having that solid industrial workforce coming back together to build the electricity that we're going to need. And it's not just nuclear. We're going to need transmission infrastructure being built. We're going to need manufacturing of all sorts of different things. And you already are starting to see it as we tried to friendshore, to use your term, on the chips, on the semiconductor fabrication stuff.
Right.
Very closely related, of course, to AI, right? Because we don't have, the United States really nowhere has, except Taiwan and a little bit of South Korea, these very, very low nanometer node, 4 nanometer fabrication technology that is necessary to actually make these H100s, now B100s, that are coming online, these large GPUs that are powering the server farms that are actually running the LLMs. So we are starting to see that there's a shortage of people just throughout the trades, throughout the economy, and both energy and actually building the chips, building the fabs that make the chips. This is sort of, I don't want to, I hate to sound so optimistic, because it sounds, I'm sure a lot of hate about being so Pollyanna-ish, but there is a world in which this is a very good thing for American and Canadian dynamism. The idea that we're actually going to go back to some of the communities that have been devastated by neoliberal policy from 1980, 1990, 2000, right? And bringing back to those communities real industrial jobs, and also giving them a pathway for people who like to work with their hands, right? Rather than just sitting at stooped over a laptop, like maybe you or I. Well, you're a physician, but I spend most of my time on my laptop, and I can work wherever I want. Right? Whereas, if you're actually doing craft or manual labor, that's something that I think could be societally good.
Right. Yeah. I mean, carry on. But,
no, I mean, I just keep on thinking about our trip to Bruce, right? Just seeing how crowded that plant cafeteria was, right? I mean, the plant was just bustling with people, and there's part of it, everyone's complaining about the lack of housing, but on the flip side, this is fantastic for these communities to have that economic opportunity that's coming in, to have new growth that is not just college-educated consultants at McKinsey and BCG, but to have people able to access 6-figure incomes without, pretty quickly coming out of school. That's a good thing for the economy. And I think what the industry needs to do is let's figure out how we can make sure that we're getting the amount of trades people that we need for the building the large reactors if we go down that route. And that's I don't know. I'm optimistic. This is what I'm excited about, is that we're actually starting to see in real life, like what we were talking about why we like nuclear so much.
It's interesting. I mean, there's certainly different flavors within the nuclear advocacy community. I would describe some people as frankly being religious. We often criticize environmentalists for sort of, this Nietzschean God is dead, but human beings are fundamentally kind of religious beings, and the environmentalists have found a new God to worship, and it's got very religious undertones or even overtones. And you see that in the nuclear world as well, and a kind of worship of energy abundance. And kind of just a love for nuclear. Nuclear for nuclear's sake is not really my motivation, certainly anymore. Like nuclear, as a means to an end, makes sense to me. Again, I am concerned in terms of, ultimately who can pay for the energy. And I do think it's going to sort of pull away and distract from climate objectives or even just everyday people's needs in terms of, who's got the dollars to pay.
Can I give you why I'm uncharacteristically optimistic about this? And people know I'm a doomer, gloom, not on AI necessarily, but on just general. I'm a Jewish hypochondriac, and so the issues that I see. What's great about this, and let me just be optimistic for one time, and make a really bullish case for nuclear, and why I'm excited is that here we have the ability for the first time that we're not demand constrained, we're supply constrained.
Yeah.
So number one, so that means that people are going to be less price sensitive than they normally would be. And all of a sudden, if they're able to say, you know what, I'm going to pay $115 a megawatt hour for carbon-free power, or maybe even north of that.
Right.
All of a sudden, we talk about coming down the learning curve in nuclear.
Right.
Or in any clean energy technology, by the way. This is not just nuclear, but if you're interested in CCS, if you're interested in geothermal, if you're interested in other renewables, battery storage, whatever. All of a sudden, we have people who will buy those first plants to start us going down that learning curve.
Right.
And that is a difference from even a couple of years ago about where we were, right? That we are going to be able to start driving down this learning curve. And that is a very different place to be than not being able to even sell that first couple of projects, right? If actually these, power prices hold, if we continue having a reasonable carbon, policy environment, or even a better carbon policy environment, then we really could start actually going down and deploying in a way that we haven't seen before.
Right. We got to wrap it up somewhere, James. This has been absolutely, as usual, fascinating. I mean, even more fascinating than part 3 of Vogel.
Part 10.
Part 10.
Part 52.
Right. Because again, I think it's just such a evolving, exciting issue, which is blowing up. I think some of the path dependencies we've been had on. Just a new paradigm is here, and it, I think, radically alters where we're going in terms of energy. Again, if you appreciate this podcast, I mean, I feel like I'm doing things that will get me canceled all over the place. Free speech, I think, is really awesome. It allows interesting ideas to circulate. If ideas are based on paradigms of 10 years ago and the paradigms change, if we exist within a culture, potentially a nuclear communications culture, which is not particularly tolerant of, again, public criticism, public discourse, a relatively new phenomenon to the nuclear industry to have people that are maybe more pro-nuclear than they are, or people who are outside of the industry commenting. I think it's good. Support us if you like the work that we do, Patreon, or you can just reach out on the website and get in touch if you want to make a bigger donation. We have more efficient ways to make that happen. Shameless plug at the end there. James, any closing final words? The final thought goes to you, my friend.
Well, I just think that this is a moment. So ignoring the other maybe societal impacts of AI, which are going to be profound and maybe negative, maybe positive, or maybe both, likely both. This is the moment that we've been waiting for in some ways, because the power demand signals are there. It's no longer hypothetical that we're going to see load growth really happening. Load growth is happening. Virginia is a harbinger. The fact that we have multiple states that are cutting, basically say we can't, meet load if we build a big data center here. We have well-financed, customers who are able to put up equity, put up cash, sign long PPAs for high power prices, for low carbon firm power. The challenge now, once again, falls to us. Can we deliver? And is it going to be microreactors? Is it going to be large reactors? I don't know the answer to that. Is it going to be SMRs? I don't know. But whatever it is, we need to be able to demonstrate that we're actually going to be able to meet that. Otherwise, people are going to go to other forms of energy, and they might be carbogenic, they might be not carbogenic. But we have an opportunity here, and now the challenge is ours. And this is going to require a full court press. It's going to require us dealing with regulatory issues. It's going to require us dealing with technology issues, with supply chain issues, with labor issues, with all of these things. We really do need to rise to the moment, and it's incredibly exciting. I think, because I think I'm the most optimistic that I ever have been. I'm terribly unoptimistic.
Right.
I don't know about the future of humanity, but nuclear power, it seems like it's having its day in the sun.
I'm just hoping that the intermittency of renewable energy may save us if things get out of hand with AI. I've told that joke too many times.
Well, that's what happened in The Matrix, of course, right?
Fill me in again. I haven't watched it in 20 years.
Well, actually, I mean, I'm not like a big Matrix fan, but like apparently it was all solar powered.
Right.
And then the humans, and to destroy the AI, basically blotted out the sun, right? To basically block the solar PVs, and then they enslaved all of humanity to use the human energy.
Because we're so power dense,
in 80 watts or whatever we have per person, right? And so, like, I don't. That part didn't make any sense.
They should have been like feeding the humans.
So maybe we shouldn't do nuclear powered.
Okay.
Maybe we shouldn't do nuclear powered AI. Maybe it should all be solar and wind, and then we can stop the wind and stop the sun to blot out the machines from killing us all.
Love it. James, great seeing you in person.
Oh, perfect, of course.
And we will connect again on the JP1000 Can Do Kids show, otherwise known as Decouple. This is our special series.
Bye.